Hey guys, IBM is here with I think this is going to be part 17. This is part 17 of magnetic fields and electromagnetic induction. Remember, these are solved past paper questions from 2001 up to around 2025. A bar magnet is suspended vertically from the free end of a helical spring as shown in the figure. Okay. One pole of the magnet is situated in a coil. The coil is connected in series with a high resistance voltmeter. So we have a complete circuit of the coil. That means if the magnet starts moving, we expect an induced EMF. So we expect a reading on the voltmeter. The magnet is displaced vertically and then released. The variation with the time t of the reading V of the voltmeter is shown in the figure. So the variation has been shown here. State Faraday's law. We have already stated the Faraday's law, but like I said, when I repeat a question, it's because I want to refer to the question. So I'm repeating this law because I want to refer to the law when answering the other parts of the question. So we know that Faraday's law deals with the magnitude. So the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Or you can say, because we are talking about a magnet oscillating in the coil, so I will say the magnitude of induced EMF is directly proportional to the rate of flux cutting. The rate at which the coils intercept, or the rate at which the coils cut the magnetic field of the magnet. That is Faraday's law. Use Faraday's law to explain why there is a reading on the voltmeter. Of course, the magnet is moving, and the moving magnet causes a change in flux linkage or causes a change in cutting of the magnetic fields. So an EMF is induced. So I will say moving the magnet causes cutting or causes change of flux linkage with a coil. Hence, an EMF is induced. So moving the magnet is going to cause a change in flux cutting or change in cutting of the field lines, and this is going to induce an EMF according to Faraday's law. Use Faraday's law to explain why the reading varies in magnitude. Of course, the rate of cutting changes, the speed of the magnet changes as an object oscillates, its speed changes. The speed is always maximum when the object is passing equilibrium. Therefore, the rate of cutting also changes. So I will say the speed of the magnet varies. The speed of the magnet varies. So the rate of change of flux linkage also varies. The rate of change of flux linkage also varies, implying that the induced e.m.f must vary. The induced e.m.f must vary because the rate of change of flux linkage changes or varies, because the rate of change is going to depend on the speed at which the cutting is happening. Then use Faraday's law to explain why the reading has both positive and negative values. So you look at the graph, you see that V has both positive and negative values. So that relates to direction. The magnet changes direction when it is going down. The induced EMF is the rate of cutting, or cutting is occurring in one direction, and when it's going up, cutting is occurring in the opposite direction. So because cutting of the field lines changes direction, it also means that the induced EMF must change sign. So we shall say that the magnet changes direction. The magnet changes direction of motion as it oscillates. As it oscillates, so current also changes direction. So the three questions, these are common questions. Why there is a reading? It's because of motion of the magnet. Why the reading varies in magnitude? Is because of the speed of the magnet. The speed varies. Why we have both positive and negative? It's because of the change in direction. The magnet changes direction of motion as it oscillates. Use the figure 5.2 to determine the frequency f0 of the magnet. So frequency, we need to find a period here. So from the graph, I think the period is going to be, I think this is 0.75 seconds. So the period T is 0.75 seconds. So the frequency is equal to 1 over period, which is 1 over 0.75. And this gives us 1 divided by 0.75. That is 1.3 recurring. So this is 1.33 recurring hertz. 1.3 recurring. The magnet is now brought to rest, and a voltmeter is replaced by a variable frequency alternating current supply that produces a constant root mean square current in the coil. The frequency of the supply is gradually increased, so the frequency is gradually increased from 0.7 f0 to 1.3 f0, where f0 is the frequency calculated before. So the magnet is now brought to rest, and the voltmeter is replaced by a variable frequency alternating current supply. So where we have the voltmeter, there's now a variable frequency alternating supply, which is now going to cause damping. Now the voltmeter is being replaced by a variable alternating frequency supply. So that means there is actually a current, there's alternating current in the coil, but the magnet is at rest. On the axis of the figure, sketch the graph to show the variation with the frequency f of the amplitude A of the new oscillations of the magnet. So now that the frequency of the supply is gradually increased from 0.7 f naught to 1.3 f naught, where f naught is f naught is going to be the resonant frequency. So this is where we expect the magnet to oscillate with the maximum amplitude, because now we are going to assume that the power supply is going to cause the alternating power supply is what is now going to give oscillations to the magnet, because this is going to create a magnetic field, which magnetic field is going to act so as to oppose that of the magnet, which is going to cause the magnet to oscillate. Therefore, as we adjust the frequency of the alternating supply, we also expect the amplitude of oscillation of the magnet to also change, but the amplitude of oscillation is going to be maximum when the resonant frequency of the magnet, which we calculated in the previous part, is equal to the driving frequency caused by the by the alternating power supply. Therefore, we shall have a resonant curve of this nature. This is a resonant curve because we have a driving system, which is now going to be the one causing or giving additional energy to the magnet to oscillate for the required period of time. So I don't want to go beyond this. I also don't want to go beyond that. The peak should be at f naught. That's where we have maximum amplitude. So the graph looks like that. I'll just rub off these ones here. Okay, that is the resonant curve. Name the phenomenon illustrated on your completed graph. So that is resonance. State one situation where the phenomenon named in Roman 1 is useful. Applications of resonance. Of course, this must have seen this in simple harmonic motion as a topic, oscillations and simple harmonic motion. So resonance of quasicrystals is used in timing. Resonance of quasicrystal. This one is used for timing. That is to control clocks. Then resonance is also resonance of quasicrystal is used for production of ultrasound. Resonance production of ultrasound. Of course, others we have microwave oven cooking. That one uses resonance. You can talk about tuning of radios and TVs. Tuning circuits of radios and TVs also uses resonance, and so many others. You can visit simple harmonic motion and oscillations to understand resonance in more details. A charged particle of mass m and charge positive q is traveling with a velocity v in a vacuum. It enters a region of a uniform magnetic field of flux density B as shown here. The magnetic field is normal to the direction of motion of the particle. If the magnetic field is perpendicular to the direction of motion of the particle, by Fleming's left-hand rule, the particle experiences a force. The path of the particle in the field is the arc of the circle of radius r. Since the arc is towards the bottom, it means when the particle just enters the field, the force is actually, the force due to the magnetic field must be downwards. So the particle is entering at that direction, the magnetic field is downwards, and the particle is entering in that direction, the magnetic force is downwards. So this is the velocity of the particle, and the particle is positive. So the second finger of Fleming's left hand rule points in the same direction. Explain why the path of the particle in the field is the arc of a circle. We have answered this question. We said magnetic force is constant and always perpendicular or normal to the velocity of the particle or direction of motion of the particle. So the speed, kinetic energy does not change, no work done. The force just provides centripetal force. The magnetic force just provides centripetal force. Okay, so I'm saying the magnetic force on the particle is constant. And always perpendicular. And always perpendicular to the velocity or to the speed or to the direction of motion. Direction of motion. So the speed of the particle, remains constant or does not change. And the magnetic force just provides the centripetal force. Show that the radius r is given by the expression that. So since the magnetic force provides centripetal force, we just equate magnetic force to the centripetal force. So this means B QV equals to mv squared over r, or you could say BQ equals to mv over r, which implies that r is equal to mv over BQ. A thin metal foil is placed in the magnetic field in B. A second charged particle enters the region of the magnetic field. It loses kinetic energy as it passes through the foil. So it loses kinetic energy, therefore the speed decreases, and of course we expect the radius of the orbit to decrease. As it passes through the foil, the particle, so it loses kinetic energy as it passes through the foil. Okay. On the figure, mark with an arrow the direction of the particle. So because it loses kinetic energy, it means the radius of the orbit, the radius of the path decreases. So it means the path should be closer to the foil when it goes through the foil. If it was to gain kinetic energy, the path would be far away. Therefore, the arrow should be pointing in this direction here, because you notice that after going through the foil, the path is very close to the foil. It can't be the other way around, because the other way around would mean if I placed it pointing downwards, it means that after passing through the foil, the path goes away from the foil, which means now the circular path becomes bigger, therefore it means the radius is increasing. But since it loses kinetic energy, the speed decreases. We know that speed is directly proportional to the radius. So because the speed decreases, the radius of the orbit must decrease. So the path must be closer to the foil after going through it. So the particle must be moving from the bottom to the top as indicated by this arrow here. So the arrow should be pointing that direction. Note that the other way around, if I made the arrow to point downwards, that the radius is increasing after passing through the foil, since the path will be farther away from the foil. The path will be getting farther away from the foil. Yet, when you consider the arrow I've drawn here, the path is very close to the foil, is getting closer to the foil after passing through the foil. So the arrow should be pointing upwards, like that. The path of the particle has different radii on each side of the foil. The radii are 7.4 and 5.7 centimeters. Determine the ratio of final momentum of the particle over initial momentum of the particle. So we note that R is equal to mv over bq previously, which means that the momentum, which is mv, is equal to bqr. When I try to find the ratio will be, of course, the b is the same, q is the same because it's the same particle. What is changing is the radius. So final momentum, final radius is 5.7. So this is going to be bq times 5.7 centimeters. Initial radius is 7.4. So this is bq times 7.4 centimeters. So the ratio is going to be 5.7 divided by 7.4, which is 0.77. A proton of mass m and charge q is traveling through a vacuum in a straight line with speed v. It enters a region of uniform magnetic field of flux density b. So the particle is positive, mass m, speed v. The magnetic field is normal to the direction of the motion of the particle. Whenever the magnetic field is perpendicular to the direction of motion of the particle, then the particle experiences a force, a magnetic force, which is also perpendicular to the direction of the velocity and also perpendicular to the magnetic field. Since the path is upwards, the magnetic force at entry is vertically upwards. Explain why the path of the proton in the magnetic field is an arc of a circle. So we have answered this question. Now we are becoming familiar with it. The magnetic force on the proton is constant and always perpendicular or normal to the velocity, and the speed is constant. So the magnetic force just provides centripetal force. So the magnetic force on the proton is constant and always perpendicular to the velocity or direction of motion. So the speed remains constant. Not the velocity, but the speed remains constant because the velocity changes because of direction. So the speed remains constant, hence I will use hence instead of so. Hence, magnetic force just provides a centripetal force or centripetal acceleration. The angular speed of the proton in the magnetic field is omega. Derive an expression for omega in terms of B, Q, and M. So we have already said the magnetic force provides centripetal force. So I'll equate magnetic force to the centripetal force. The magnetic force is given by B, Q, V. Centripetal force is mv squared over r. So this means that BQ equals to mv over r, and for circular motion we know that v equals to omega times r. So this is going to imply that BQ equals to m omega r divided by r. So this means that BQ equals to m times omega, or you could say that omega equals to BQ divided by m. State the relation between the magnetic flux density B and magnetic flux phi, explaining any other symbols you use. So magnetic flux, you know that phi equals to BA sin theta. B has been defined, phi has been defined. It's only A which has not been defined. So A should be equal to the area normal. A equals to the area through which the flux. Because I used the sine theta, I would say A is the area through which flux passes. Area through which the magnetic field lines pass. And then theta is actually the angle between, because here I've put sine, theta should be the angle between the magnetic field and the plane of the area. If I had used BA cos, if I had said magnetic flux equals to BA cos theta, theta would be the angle between the magnetic field and the normal to the area. But since I've used BA sin theta, then theta is the angle between the magnetic field and the plane of the area. So if this is the plane of the area, and let's say the magnetic field is in this direction here, so the angle is theta. When I resolve it to the vertical, because we always need it to the vertical, this will be B sin theta. So if I was to take this angle here, it would be B cos theta. Alternatively, I could say magnetic flux equals to BA. I ignore the sin theta, but I will just say A equals to the area normal or perpendicular to the magnetic field. So I could say magnetic flux equals to BA. Because B has been defined and phi has been defined, I would say A is the area normal to the magnetic field. A large horseshoe magnet has a uniform magnetic field between its poles. The magnetic field is zero outside the space between the poles. A small hole probe is moved at a constant speed along a line xy that is midway between and parallel to the faces of the poles of the magnet as shown here. An e.m.f is produced by the Hall probe when it is in the magnetic field. The angle between the plane of the probe and the direction of the magnetic field is not varied, so the angle is remaining the same. On the axis of the figure, sketch a graph to show the variation with the time t of the e.m.f Vh produced by the Hall probe. Of course, we know that outside the poles, because there is no magnetic field, the Hall voltage is going to be zero because Vh is equal to Bi or sine theta divided by Nt cube. If outside the poles there is no V, then there is no Hall voltage. So outside the poles, the line is going to be along before it enters and when it leaves, the line is going to be along the x-axis. But then, very close to the poles, there's a strong magnetic field. So the Hall voltage raises to a maximum value, and then when you move from the poles, or when you go outside the poles, it also now changes or it decreases rapidly. Because if inside the poles, the magnetic field inside here is uniform, so the VH is going to be uniform. It slightly changes on outside when you are getting out and when you are coming inside. So I'll just draw a graph here where it's going to be along the x-axis outside the poles. But then it um, it rapidly increases and decreases between the poles. It is actually uniform. So I'll draw a horizontal line here, uniform and not zero, because B is not zero inside the poles. There's this rapid change from zero to a certain value and rapid decrease to zero when you move out of the poles. So I'll draw this as a sharp the line with a steeper gradient there, and another line with a steeper gradient here. It is something like that. Okay. State Faraday's law. Like I said, whenever I restate the law, because I want to refer to it when answering the next parts of the question. So Faraday's law states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage or rate of flux cutting. Magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Rate of magnetic flux linkage, or the rate of cutting. The whole probe in B is replaced by a small flat coil of wire. The coil is moved at constant speed along the line XY. The plane of the coil is parallel to the faces of the poles of the magnet. On the axis of figure 5.3, sketch a graph to show the variation with time t of the induced EMF. Okay, now that we have a coil of wire and we expect an induced EMF, we know that the induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is directly proportional to the gradient. So EMF is directly proportional to the gradient of the graph of VH against T. So where the gradient is constant, the EMF is constant. Where the gradient is zero, the EMF is zero. So here, between t equals to 0 and before we enter the poles, we see that the gradient is constant and 0. Here outside the poles, constant and 0. In between the poles, the gradient again is constant and also 0, but it only slightly changes at the point of entry and at the point of leaving. And at entry, it is still a straight line, so the EMF is constant. At exit, it is still a straight line, the EMF is constant, but not 0. So the EMF, before the coil enters the magnetic field, it is 0. So we're going to have a horizontal line. Let me increase the thickness. So before entry, we have the induced EMF is 0 because the whole voltage is 0, or there is no magnetic field. And also outside, there is no magnetic field. The whole voltage is 0, so the induced EMF is 0. Inside, the magnetic field is constant, so still there is no change in magnetic field. So it means the whole voltage is also going to be induced EMF is 0. But at the point of entry and exit, there's a change. It changes to maximum and constant, then it decreases back to 0 when you are leaving the magnetic field. So here, the gradients, you notice that the gradients are, this one is positive gradient, this is negative gradient. So the EMFs represented by these two sections are going to have opposite signs, but approximately the same value. So we shall have a spike at the point of entrance. It should be very narrow here, but because I'm drawing on a computer, it may not be very narrow as I wanted, but you can make it very narrow here. The same thing happening here. Okay, so it's something like that. The EMF is constant, jumps to a constant high value, but in a very short period of time because the gradients are very steep here at entrance and exit. So this is the graph of the induced EMF against time. I think part 17 should stop here. Until next time, bye bye.